This is Calculus, continuing to talk about anti-differentiation, integration, and now working with differential equations. So today I want to take a look at an application and how integration can help us solve an application question. Questions like this are just very common on the AP test, and we want to be familiar with different ways of looking at it, different notations, and in fact, ways to solve them on the graphing calculator. So that's what I'd like to do with this one is first of all interpret it. So it says water's leaking from a tank at a rate given by this expression. And that is in gallons per hour. So a big thing to watch for, not only when you're working through homework exercises today, but also on the AP test, is pay real close attention to your units. It says we're working with gallons per hour, which is telling me this is a change in volume over a change in time. So I just introduced a differential. Remember, a differential is just notation for a derivative. But this would work out for this. Like dv dt could be said to be negative 0.1 t squared, and then so on and so forth. So let me get this down. Okay, so here's this differential equation if I want to look at it this way. And now they're asking me how many gallons will leak out in the next 3 hours. So something to kind of keep track of here. This is a lot like our motion by velocity kind of discussion that we've had most of this school year, where we know when I'm looking at a velocity equation, anytime a velocity is on the positive side of the x-axis, so if this is v of t and this is t, all throughout this time I would be moving in one direction. But if I have a x-intercept and a region of the graph which is below the x-intercept, this would indicate negative velocity, which would mean I changed direction. So one thing to be very careful about is don't always assume that the integral of a rate of change is going to be a total amount of change. In fact, in this case, if I were to integrate from, let's say, a to b all the way across here, say b is out here, we know that the integral from a to b here would not be total distance traveled. So I just want to make sure that you remember that, and that would be because, you know, this negative direction motion and some positive direction motion would cancel, and instead this would give me the change in position from A to B, right? There's a difference, change in position. Okay, so because we would be going forward for a while, and then for a short while we would be going backwards, so it might be something like, okay, envision the motion detector here. Tick, 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 right? And Joe is walking. Boop, 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 boop. Okay, and Joe goes away for a while, and then he comes back for a short amount of time. So what your integral would represent here would be the change in distance from when he started to when he ended, from A to B. So it's one thing to kind of keep in mind as how does that same idea show up in other relationships. Like in this case, we have water leaking from a tank. In this case, I don't think we have to be concerned about it because they never talk about the volume increasing and then decreasing. This is all water leaving a tank because it's apparently leaking. So in this situation, I don't really have to worry about, you know, like water coming back into the tank or water going in and out of the tank. This is simply water coming out of a tank due to some sort of leak. So, long story short, if I need to know a change in volume, if I were to integrate volume with respect to time, that would be like integrating from 0 to 3. So over the next 3 hours, assuming that time 0 is at the beginning of the leak, I would have this integral. Okay, so if I integrate both sides, I end up with a volume as being equal to, well, in this case, it's a definite integral, so I won't have like a plus c or anything, but I would just integrate this, and this would be a great time for us to maybe take a look at using the calculator feature to evaluate a definite integral. So this time I'd like you to use, instead of graphing this one, I would like you to go number 1 in your math menu. So if you're looking for that on the graphing calculator, that's on the left side, about 4th button down. And then I want to say it was number 9 to use your function numerical integration. And function numerical integration, fnint as I always call it, fnint there, okay, is a numerical method by which a graphing calculator will approximate an antiderivative, a definite integral. Okay, so I'm sure that you guys are familiar with it. I'd like you to evaluate this, and you'll find that the volume change that happened, let me see if I type this in, is about 3.75 gallons. Okay, so that's really very common both on the calculator and non-calculator sections. This would be a good example of something you might see on the calculator section of the AP test. Alright, so we just worked with a differential equation in context. Today I really want to look at the differential equations that go along with our current section of integrals. I want to look at any differential equation, however, that might show up. And sometimes, remember, a differential is just any symbol that represents a derivative. So it might just be dy dx. It might be dv dt, like we looked at in the last example. It could be just about anything which represents a change in one quantity over a change in another quantity. And that sometimes is just two variables random, and sometimes it has physical meaning. In this case, this is actually considered a differential. I have f prime is given to be 2x plus 5, and they gave me f of 0 equals 3. And remember, they use this phrase, find a particular solution to a differential equation. So all that means is that if I want to find f of x, I will need to take the integral of f prime, and this isn't going to be a definite integral, this is an indefinite integral. Okay, so we'll just evaluate that, which means, but this isn't entirely true. I'm going to have to then solve for c, right? I'm going to integrate, then find c using the solution point that's given. Okay, so we've worked with these before. This is this is actually a question that I think we saw very early in chapter 4. I'm just going to integrate this bad boy real quickly, so I would end up with x squared plus 5x plus c. Okay, and then if this is what f of x is equal to, the solution point plugging in 0 for x will give me a y value of 3. I think that's pretty easy to see, implies that c equals 3. I don't always assume that the initial is going to directly give you c, but in this case, that one's pretty easy algebra to see. So our general solution, or our particular solution to this differential equation, in this case, the solution is f of x equals x squared plus 5x plus 3. Got it. Okay, so what this represents is the particular solution to the differential equation such that this solution point exists. Don't forget what the various equations actually mean. Like, don't forget that this is an equation which gives me the slope of every tangent line to this graph, right? So if I asked, what is the slope of the tangent line at this point 0, 3, I think you guys would know that means I'd find f prime of 0, and f prime of 0 would be equal to 5. So the slope of the tangent line at that point would be 5. Okay, so differential equations a lot of times are in the context where they also give us a slope field. Remember what a slope field is. These are little unit vectors which tell us about the slope that this family of curves has for any particular x value. So quite literally, I could say, without even looking at this equation, just looking at the picture over here, I might be able to come over here and say, well, at about -3/2, 1, it looks like the slope of the tangent lines would be approximately 1, because I'm looking at this little unit vector and thinking it looks like it rises 1 and runs 1. I'm just estimating. So kind of keep that in mind. Sometimes on the AP test, you have to generate these slope fields. Sometimes you have to use them like we've had some experience doing. So on this one, let's find a particular solution. To do so, that means I'm going to be finding the integral of, that's one messed up integral symbol. I'll be finding the integral of dy equals x cos squared x cos of x squared dx. Got it. Alright, so if I integrate both sides after I separate my variables, so what I've done there is I moved dx over, and this is called separation of variables. It's going to be very important as we move ahead that we actually have to go about the symbolism this way, and you'll see why in the future. If I integrate the left side, I just get y in terms of x. And if I integrate the right-hand side, I realize, ooh, now this is going to be a little harder. I do not have just a basic polynomial with pluses and minuses of terms. So this looks like a opportunity for u substitution. If I let u equal x squared, wow, I'm making a mess here. If I let u equal x squared, then du would be equal to 2x dx. As you can see, I do not have the 2, so I'll slide that over. I have a 1/2 du is equal to x dx, and this just became the integral of 1/2 cos of u du. Alright, so the integral of cosine is sine, and I have 1/2 sine, and I can back substitute for what x was equal to, or what u is equal to, is x squared. And then, of course, I have my plus a c. Okay, so I have all this going on. This is y in terms of x almost. One thing that we'll start to see as we move forward, we're going to have a little bit more difficult slope fields and a little bit more differential equations that take some additional steps. So some domain and range issues might show up. But on this basic example, this cosine doesn't have any domain issues. If this was tangent, we would have vertical asymptotes and various other domain problems that maybe we would need to consider. In this case, we're given a point. This is a solution point, 0, 1, which apparently makes this true. So if I put 1 in, I have sine of 0 squared, so that's sine of 0. Keep in mind that when you're finding sine, you're finding y values after 0 rotation would give me a y value of 0 times 1/2 is still 0, so c equals 1. So y in terms of x would be 1/2 sine of x squared plus 1. And there is my particular solution to the differential equation. Now, as you know, usually when you're presented with one of these nifty slope fields, you're challenged to draw that particular solution in. So it's been labeled here 0, 1. Reminder that what you do here is you're trying to draw your graph in such a way that you always stay parallel as you pass any one of these little unit vectors. So this can be challenging, especially when they give you one where you may not actually hit these segments. So I'm saying as I move to the left here, I'm forced to keep this parallel. I'm not going to hit this segment. And it looks like this is a horizontal tangent, so as I come this way, I'm trying to be a little bit steeper as I pass this up here. So I just try to whoop, and then, oh wow, I'm going to have to make a sharp turn to be heading back downwards. So there's that heading back downwards. It's looking pretty steep. Now wait a minute, I got to be turned and back up, growing quickly by the time I get there. So I make that change. Now it looks like this pattern is going on and on and on. So let me try to do that. Whee, that was nice. Okay, and the same thing going off to the left direction. Now I'm starting to realize maybe I have the symmetry here and the function itself shows some symmetry, so it'd be good if I could try to actually be a little bit symmetrical. That wasn't that great right there, but not terrible. And done. Perfect. Okay. Well, all right, not perfect, but at least I have what I think is an acceptable graph of this particular solution. Remember, if you're asked to do just any other general solution, you just pick some other starting point and then potentially draw an exact replica of what you already drew, staying parallel through your, whoops, that would be bad, but you get the point. You might have any other spot where you pick to start, and then you're going to end up with a vertical shift, essentially, of this green graph. Okay, so that's working with differential equations involving u substitution. It won't take much practice with this, and you'll have a handle on it. Also, make sure you're practicing on the application questions using the graphing calculator. You need to be very good at it from both the math menu, and then secondly, you know that you can use the integral, the definite integral function, which is from the graph menu if you have it typed into y1 and you're looking at a picture. Okay.